Hello everyone again and welcome to our machine learning tips. So in our previous video, we did look at the applications of K-nearest neighbor, and I mentioned that it was a supervised learning technique where we can use it for both regression and classification based problems. So today we will be seeing how we can use the K-nearest neighbor algorithm to classify tumors as a malignant or benign using the breast cancer data set from scikit-learn. This data set is originally from what? The UCI Machine Learning Repository. We already used this data set when we did logistic regression. So you can go back to that lesson and try to see how we can download that data set if you do not want to import it from the scikit-learn library. So by the end of this lab, you will be able to load this data set from scikit-learn and then apply the KNN classifier from the scikit-learn library, and then we evaluate the performance of that model using the accuracy score, and then we will also see how changing K affect that model performance. So the first thing is to import these libraries. We are going to import the pandas. We already know the use of panda, and then I did mention that we are going to be importing that library from the scikit-learn, the data set from the scikit-learn data set, and then we going to from scikit-learn model selection, we will import the train test split to be able to cut that data into training and test set. And then because KNN uses a distance measure to be able to learn, we are going to be importing the standard z-score to be able to scale that data to a particular range. Also, from scikit-learn, we are going to import the k-neighbors classifier because it's a classification problem. If it was a regression problem, we are going to be importing what the k-neighbors regressor. And then also from scikit-learn, we'll import the accuracy score. We will import the classification report to be able to see the precision recall and so on. And then the confusion matrix, which is a table to show the true positive rate, the false positive rate, the true negative rate, and so on. And then still, we are going to be using matplotlib to be able to see how the model performance changes over different values of K. And then we run this. So that has already, we run our libraries. The next thing is we are going to load our data set. Now, we are importing that data set from the scikit-learn data set. We load the breast cancer data, and then we load it. So if we do .head, as we have always been doing in previous lesson, it will just show us the first 5 rows in that data. One thing we should note here is that, this data set has 569 samples, which is rows. There are 30 features, and then we have a target variable, which is distinguishing whether the breast cancer is going to be what, malignant or benign. Then when we load that data, the next thing we are going to do is, a good practice is to cut that data into training and testing so that we use the train set to be able to enable that model learn the patterns in that data, and then we use the test set to evaluate the model performance after it has learned that pattern, and then it will be able to classify the cancer tumors into what, benign and malignant. One thing we should note here is that the training data has 455 rows, and then the testing has what, 114, because we cut that data into what, into 80% for training and then just 20% for what, for testing. Now, KNN relies on distance metric, as I did mention earlier, to learn. So we are going to standardize these features so that they fit into a particular scale. We already learned the different normalization techniques. So here we are going to be using the standard z-score. So when we cut that data, we standardize it. The next thing is to do what? Is to train that k-nearest neighbor model, which here we are going to using the k here to be equal to 5, and then we evaluate that performance and see how it is going to perform for this value of k. One thing you have to note here is I did mention when I posted a video on the k-nearest neighbor that for a binary classifier, avoid using the value of k to be even, like k equals 2, 4, and also avoid using the value of k is equals to 1, because when you use k equals to 1, the model might overfit, meaning that it will perform well on training and might not perform well on the test set, meaning that on the data that the model didn't see during the training process. We are going to run this. One thing you should note here that we are importing, calling that neighbor classifier. We are the number of neighbors here is what is 5, and then we are feeding the train features and the labels. And then now the prediction here, when we have trained our model, we want to see how it performs on data that it didn't use during the training phase, which is the test data. And then we are going to look at the accuracy of that model. So this prediction here will give those predictions, whether it belongs to the benign class or what, or the malignant class, which is benign is 1, malignant is what, 0. So now we are looking at the accuracy score here, which is that for the test and what the predictions. And then we run this, as I did mention, we are going to see when k is equal to 5, the accuracy score is around approximately 96%. Also, when we look at the classification score, we see how that model is performing, both using precision recall and the F1 score. One thing you should note here that out of the 114 samples or rows for the test set, 42 of them were what? Malignant, and then 72 were what? Belong to the benign class. So the confusion matrix here actually shows a table how that model will perform. So 39 here simply shows that out of the 42 malignant class, the model got 39 of them right, meaning that the true positive rate, true positive here is what, 39, and then the false positive here is what, 3, meaning that it only misclassified what, 3 out of the 42. And then for the benign class, out of the 72, the model got 70 of them right, meaning that the model is actually performing well on that test set. So now we do not only want to end there. One good practice in k-nearest neighbor is always to do what? Is always to try to plot the model performance using, you can use the accuracy score, precision, whatever score you're trying to use. It's always good to see how that model is going to perform for different values of k. So here I'm using k as 1, 3, 5, 7, 9, 11, 13, and 15. Remember here I'm not using k as any even number for reasons as I did mention earlier. Now, if I run this, now we can see here that, when k is equals to 1, the model's accuracy is approximately, 94%. And then when k is equals to 3, that accuracy is around 98%. We can see here that the best performance is when k is equals to 3. Also, we are plotting this so that you can see that visualization. We see that when k is equals to 3, that model performs much better compared to when k is equals to 5, k is equals to 7, k is equals to 9, and then so on. But one thing we have to note here is that when k is from 7 and above, the model performance stays consistent. So as a quick experiment, one thing you can try is to change that train test random state into something else. Maybe you change it to 0.3, saying that you are giving that the training examples to be like 70% and the test to be 30%, and see, retrain the model and see how the accuracy is going to look like. One thing you can do is to go remove some features. Maybe you use only those features that have mean attributed to it. Like if we go back to the data set, we can see some of the features can have the mean radius, the mean texture, mean parameter, mean area, mean smoothness, and so on. And then also, one thing you can try is maybe try different scalars. Maybe we already use the standard scalar. You can use the min max normalization technique. And then also, whereas you can also train that model without scaling and then compare the performance of that model and see how it's going to look like. Guys, that was it for this lesson today. Keep following me both on YouTube and Facebook for most of these machine learning tips. Thank you.